Hello everyone. Today I'm going to be showing you how to use TotalLab's new Phoretix 1D image analysis software to analyze an image of a Western blot and quantify the bands within it. So the first step in our analysis is actually importing the images that we want to analyze into our copy of Phoretix 1D. Now, because Phoretix 1D is not associated with any particular equipment manufacturer, it's open to all equipment manufacturers. So any image that is exported in a .tiff, .png, .bmp or .jpeg file format can be analysed using Phoretix 1D. And this covers all modern gel documentation devices, densitometers, scanning devices, and even things like mobile phones and digital cameras. As long as they can export in one of those file formats, our software can analyse it. So it's as simple as coming up here and left clicking open, and then clicking our image, opening it in, and you'll have imported your image. So I'm using the Windows version of our software at the moment, but we do also support Macs with Phoretix 1D, so you can get a Mac compatible version of this software and it works exactly the same. I'm just using it on Windows because I use a Windows laptop. So once you've imported your image, you're given these three different image windows. So at the top left here, you're given a false color view of your image. And in this false color view, you'll see that some of the bands are actually colored in orange. And this means that those bands are saturated. And what I mean by saturated is that the intensity of those bands is beyond the limit of detection for the scanning device, the gel documentation device that this particular gel was imaged on. So it informs the operator right away that the results that they're going to achieve with these different bands are not going to be accurate. They are going to be arbitrarily cut off. So this tells the operator if they're particularly interested in these bands, they need to go back and re-image their gel, or they need to exclude them from their analysis, or they need to be aware that they're not going to be getting true representations of the values of these bands, rather than going through the full analysis and thinking that they are seeing the full picture because they're not in this instance. So that's a really quick, handy way of identifying to users that the image that those bands are saturated and they're not going to be a true representation of the results. To the right of that image view window, we have this 3D view, and if you left click and drag around, you can manipulate the 3D view to have a look and inspect your blot or your gels. You can also left click here and to see a maximized view of this 3D view for better inspection. You can also right click on this image and copy it to a clipboard or save it to a file to then import into other pieces of software. So these images are really handy for including in presentations, papers, posters, because they're a really striking visual way of portraying the results that you've got on your blot or your gel. And at the bottom here, we've got the typical grayscale image view. Now, if you left click on this button, you get full control over being able to change the contrast and the gamma for your image. So if you wanted to try and identify very faint bands, you might want to manipulate your contrast to make those more visible, or change your gamma to change the kind of the brightness of the image. You can also apply many different layers of false color to your image. So if you're using a multi-channel image, or if you're trying to create a multiple channel image and you want to assign your channels particular colors, you can do that with the false color view. We've got false silver stain and Kamasi blue colorings, and my favorite is the heat map view. So this kind of thermal vision predator type view. So this is really good at finding faint bands within your image, because it colors your bands this bright green color, the bright red color, and the bright blue color. There's a huge contrast between those different colors, and it allows the human eye to pick out very faint signals that might otherwise be lost in kind of your standard grayscale image. These false colors are also handy for anyone that suffers from color blindness. So if there's a particular way that gels or blots are being displayed that is difficult for them to see, you can simply change the color and kind of allow anyone with any kind of color blindness to be able to see the image correctly. We've also got the ability to rename the channel. So you might want to give it your experimental name, or if you're using a multi-channel image, you might want to name your channels after, say, housekeeping channel, protein of interest channel, that kind of thing. So once we've imported our image and we've made sure that our kind of contrast and gamma settings are correct, and that we've applied any heat map, any kind of color, false color maps that we want to apply, we come through to the lane section. Now, Phoretix 1D employs an automatic lane detection algorithm. So in the majority of cases, it's as easy as coming onto your lane section and left clicking the big blue detect lanes button. And as you'll see, your image has been populated with your lanes. Now, within this image, because we've still got the wells at the top of the image, it's the algorithm has detected those as bands. So it's not cut those out when detecting our automatic lanes, but we've got a tool to sort that out. So if we left click here, use AOI, which stands for area of interest, we get this purple box. And we can stretch out the handles of this purple box by just left clicking and moving them around. And this will inform our automatic lane detection algorithm where to look within our image. So if I left click again, you'll see that it's excluded the wells from the top of the image and only included the bands in our lane detection algorithm. Now, we do have the ability to define areas of interest within your automatic lane detection is fantastic for multi-tier gels, where you've kind of got different sections of your image where you've got lanes, some where you have, some where you haven't, and you want them to be considered separately as kind of separate analyses and things like that. We've also got a full suite of manual lane editing tools, but I'll go through those in a separate tutorial video. So once we've identified our lanes within our image, we then move through to our background subtraction. So obviously, we want to remove the background signal from this image so that when we're analysing our peaks, when we're looking at the intensity of our bands, we're only getting a true representation of the value of the band from the peak to the bottom rather than from the peak to the background. So as you can see here, as I move my lane along, you can see that it also moves on the image as well, so I can see my various different peaks. So if I come to the right hand side here in my define background section, we've got a few different ways of doing background subtraction. It'll all depend on your image and your usage. But for the majority of cases, we would recommend using the rolling ball method of background subtraction. So as you'll see, when you do select a method of background subtraction, this dark area appears on your lane profile view here. This is what has been calculated as the background. So this is what is going to be removed from your image. And what you want to do is to make sure that this shaded area, this area that is going to be removed, is an accurate representation of where the background is. So your settings here will inform where this shaded area is, and what you want to make sure is that this shaded area does not remove any of your peaks, but also kind of cuts off at the bottom. And again, I'll do a tutorial video on background removal and what techniques to use and how they work and things like that separately outside of this. And if we left click display background, you'll see just the peaks that match up with the lane slice here at the bottom, and then turn it on to see what your background settings have actually removed. Now, I'm obviously just looking here at channel 1, lane 1. If you want to access your different lanes, you can view them all at once, or you can view them all separately to see how your background removal settings are going to look on every lane. Because your background is not even throughout your entire image, applying a global background removal setting to every lane will have slightly different effects on every lane. So you just want to make sure that for the majority of your lanes, this background removal subtraction is going to be appropriate, and that you're not removing any of your peaks. You're only removing kind of the flat underlying area. We've also got, when you move through the next couple of steps from background to molecular weight to bands mode, we've got this zoom window at the bottom. So if you left click here, it will open up, and if you left click and draw a box around the area that you want to look at, you can see that my image view on the left hand side, it moves around. So it's a really handy way of panning around our gel. And if you want to reset the image zoom, you just click there. And if you want to reset the zoom on this, on the profile view, you would just click this button. So now we've defined what settings we're going to use to remove our background noise. If we come through to our molecular weight calculation, so presuming that your gel or blot has been run with a molecular weight ladder, and I'll just select one of these lanes here. So presuming, as is standard, that you've run your gel or your blot with a molecular weight ladder, either on the left-hand side or on both sides, or sometimes on both sides and in the middle, we're going to tell the software what molecular weight ladder we've used so that it can work out the molecular weight sizing of all the other bands that are present in this image. So if you left click on edit templates, you can create your own molecular weight template and give it a name and tell it what kind of units it's in, whether it's kilodaltons or base pairs or something like that, and how many steps there are. So you can create those and save those within the software yourself if you're using custom-made molecular weight ladders. Or we've included a couple of big brand name molecular weight ladders that are typically used within the lab already within the software. So if you're using one of these, you would just left click on them and then left click on the lane that contains your molecular weight ladder, and it will automatically detect the lanes within, automatically detect the bands within that lane and assign them a molecular weight value, and then it will read off all the values for all the other bands within your image. So when you have assigned a molecular weight ladder, you will get this curve. So this calibration curve is a representation of how well your molecular weight ladder has run, basically. And what you want to be able to do is you can determine the fitting method used for this curve, and it depends on what molecular weight ladder you use, what fitting type you would use, but you want the R² value to be as close to 1 as possible, and that will inform that you've used the most accurate curve fitting type. But I'll go into that in more detail in a separate tutorial video. So now we've given the software a molecular weight ladder to use to work out the molecular weight of all of our bands. We come through and left click on our bands mode. So like we've got automatic lane detection within Phoretix 1D, we've also got automatic band detection to make this as quick as possible for the user. So we've got a couple of detection presets. So we've got the default detection preset, which is essentially kind of a manual mode, or we've got detection presets that are designed for faint bands or intense bands. So depending on whether you want to pick up the faint bands or pick up only the strong bands, or kind of manually edit your band detection parameters, you've got all of those options available to you. But I'm just going to go ahead and go for the low intensity bands, and as you can see, the detection preset is run every time you change it. So as soon as you click one of these modes, I've already got my bands through, and I'm starting to build up my table full of my results here. Now, if there was a band that if I show you one of the lanes where I've run band detection, you'll see that the lanes are brought up in these multiple colors, but sometimes a band may not be detected. Now this is because I've only selected high intensity, but if you wanted to manually add a band, all you would do is left click, drag, and that band would be added. Or you can right click on a detected band and delete it. You can split a band into multiple bands. So you can do that on the profile view, or you can do that on, you can right click to remove, left click to add in the image view, whichever you prefer. Gone through and identified all of your bands, then we can move through to a few more experimental specific options that are based within Phoretix. So the first one is the ability to normalize your bands to other bands that are present on the gel or blot image. Now, if you've got a multi-channel image, Phoretix 1D gives you the option to normalize channels to housekeeping protein channels or total protein channels. But when we're using a single channel gel, such as this image I've got here, the only option available to us is single band normalization. What I mean by that is we select a band out of all of our detected bands and we set that as our kind of a positive control or 100%. So if we set one of these bands as 100% or 1000% or 100 picograms or something like that, it will then express every other band in our gel image as a percentage of that, as a fraction of that. So I'll just go through and show you what I mean. So you've got two options here. We can left click a band and then use the selected band and it will be listed here and give that a value. So I'm going to give that a value of 100. So it's like 100% or one fold. And then if I just come down to my table and turn on my normalized volume, you can see this is giving me the volume of every band relative to the band that I've selected as my 100%. So because it's 100 and it's 100%, these are fractions thereof. So for this band, it would be 36%. And what it means by that is that the volume of that band is 36% of the total of my selected normalized band. And normally for your normalized band, you'd use kind of a known mass or a known protein or a positive control or a protein that you know the regulation of, like a control protein. So then if you wanted to look at the changes in protein between different experimental conditions, you'd have your control, then you'd have your, say, drug X treatment, and the protein would be 10% higher or 90% lower or something like that relative to your normalized band. Now what you can also do is simply select automatically the largest band in the gel and set that as your 100%, as your maximum, and then everything will be represented as a portion of that. Now just because I've selected this as 100% doesn't mean that, well, I've selected the largest band here, but if I had selected a smaller band and done my normalization to that band, you can see that it will go above that normalized value. So I've got 162% here for this band, which means that compared to my normalized band, this has actually got 62% higher volume than my normalized band. So that would be kind of a 1.6 times value. It would be an increase in the expression of that protein. So it's not just a decrease, it's an increase that we can measure as well. So those are the options that are available to us in terms of normalization for a single channel image. So if I come through to the next step, which would be quantity calibration. Now this requires the inclusion of at least 3 known standards within your gel or blot. What I mean by that is, say, let's take these 3 bands here. Or sorry, let's take bands that have moved down. And what I want to do is, say if I had a known protein concentration of 100 picograms, 50 picograms and 25 picograms. If I left click these bands and add them to my quantity calibration, say the first one is 100 picograms, say the second one is 50 picograms, just type into that box there, and then say this one is 25 picograms. So you can see as soon as I've got at least 3 known quantities and I've given those quantities to the Phoretix 1D software, it will start building up this calibration curve. And you can select the different line fittings, the different mathematical equations to draw this line for your calibration curve, to determine how it's going to calculate all the quantity for all of the other bands that are in the gel. Now you can add as many standards as you like, however 3 is the minimum to form that curve for which every other band is read off. And again, when you're selecting this fit type, this curve fit, you want this R squared value to be as close as 1 to 1 as possible. Now, it doesn't make much sense at the moment because I've just picked random bands and random values. But what you would do at the start of your experiment is obviously include samples that you knew the protein mass of, protein concentration, the number of base pairs if you're doing an RNA DNA gel, and that's how you would determine the kind of the quantity of protein or RNA or DNA in each of your unknown bands. So if you wanted the results to show up at the bottom here, you would left click your choose column section and then just put quantity calibrated volume. So this would give me, so again, I put in 150 and 25 picograms of protein. So this is giving me an expression of how many picograms of protein are in all of my unknown bands that are in my gel. And then if you are using standards and you do need to perform quantity calibration, that's how you would do it. And then finally, we come through to the results section. And this is where you can export all of your results in either an Excel format, CSV format. You can copy it to your clipboard as a table. And you can do that separately for your band information and for your lane information. You can select which lanes you want to include, so you can click all lanes, or you can export only the results of certain lanes that you're interested in. And if you left click here, you'll generate a PDF report, or you can generate a CSV table. So if you want to export these results to another piece of software, a CSV file is usually the best way to do that. It's a very open format, it's an Excel format. It's very easy to import into kind of stats packages and things like that. Or if you want a PDF report, you'd simply click Generate PDF Report, give it a name, so YouTube demo, how about that for this one? There we go. And this is what you'll get out at the end of it. So this is our PDF report. It's got obviously some information about the acquisition date and the exposure time used for the imaging device to use to create this image. It's got a picture of your image. It's got Phoretix 1D down the side. It's shown that you've used automatic lane detection. It shows you where all of your bands are and your background removal method. The different kind of molecular weight ladder that you used, how many steps it's got, etc., etc. And you can add more information than this to the report. This is a very bare bones report, but you can also include, depending on which options you pick on the side here, whether you want channel detail and lane detail, you can get slices of the specific lanes themselves with the profile. So I'll just generate a second report and show you how these results have changed how this report looks. So it's just going to take a couple of seconds to compile the PDF. So as you can see here, this report looks much the same in the beginning. However, when we come down to the lane detail, you can see that it's got the lane profile for every lane that was selected, where we've included our bands, the volume for those bands, the calibrated volume for those bands that we did with the quantity calibration as I just showed you previously. It's a very comprehensive report that is kind of exported from Phoretix 1D. So anyone reading this would be able to repeat your what you've done as part of your analysis. So that's how you would go through and analyze a Western blot or a gel image and turn your image into quantifiable data that you can use to prove or disprove your null hypothesis, which was the whole reason you were doing your experiment anyway. Thanks for watching. And if you'd like to test out a free trial of Phoretix 1D to see how it works with your data, please check out the links in the description below.